Imagine you have a group of students who aren't the best at a particular subject. Individually, they might only answer a few questions correctly. But what if you could train them to work together? Well, that's the core idea behind gradient boosting. It's a machine learning algorithm that combines several weak learners, like those students, into a much stronger learner. So gradient boosting takes multiple models that aren't very good at learning and combines them into a much stronger learner. Each new model is specifically trained to improve upon the mistakes of the previous one, resulting in a more accurate overall outcome. So here's how it works. Using the analogy I have mentioned previously regarding the group of students, we start with a simple model. This can be represented by one of the students who might only get a couple of answers right. Then we see how wrong it is. This suggests figuring out how much each prediction missed the mark. After, we train a new student who focuses on correcting the mistakes of the first one. Then, ultimately, we team up by combining the predictions of both students to get a better overall answer. And lastly, we do it all over again. We keep training new students to address the remaining errors, building a stronger team with each step. Gradient boosting is particularly useful for two main tasks. Regression, which is making predictions like figuring out future stock prices or which emails are spam, and in classification, which is sorting things into categories like classifying images as cats or dogs. With these kinds of functions, it is very useful and easy to use in various fields and industries. In financial forecasting, gradient boosting can be used to predict stock prices and loan defaults. In retail and e-commerce, it can be employed to recommend products to customers, predict demand for items, and optimize pricing strategies. In computational biology, gradient boosting algorithms are used for tasks like protein structure prediction and drug discovery. In natural language processing or NLP, it can be used for sentiment analysis, spam filtering, and machine translation. And lastly, for medical diagnosis, gradient boosting models can assist by analyzing patient data and predicting disease risk. Now let's delve into the roots of how the gradient boosting method came to be. In 1988, Michael Kearns had a vision to develop a powerful algorithm that transforms weak learners into strong ones. With this, the concept of boosting emerges. The idea is to combine multiple not-so-great learners to create a much better overall learner. Think of it like a group study session where everyone benefits from sharing knowledge. In 1995, AdaBoost, formulated by Yoav Freud and Robert Shapiro, made its debut. This is a major breakthrough because AdaBoost, or adaptive boosting, is the first successful boosting algorithm to gain widespread use. Imagine AdaBoost like a teacher who focuses on helping students struggling with specific topics. It gives more weight to challenging examples, ensuring everyone gets the support they need. Then, in the late 1990s, gradient boosting appears. Leo Breiman enters the scene, building on boosting's foundation. He explores its connection to gradient descent optimization, a powerful mathematical technique. And around the same time, various figures contribute significantly. Jerome H. Friedman developed specific algorithms for regression problems using gradient boosting. Lou Mason, Jonathan Baxter, Peter Bartlett, and Marcus Freon introduces the concept of functional gradient boosting, viewing it as an iterative process. Today, gradient boosting is a powerful machine learning technique combining elements of gradient descent and boosting. It tackles various tasks including prediction and classification, making it a valuable tool across many fields. There are some differences between AdaBoost and gradient boosting. First are loss functions. Gradient boosting is more flexible, allowing for a wider range of loss functions compared to AdaBoost's focus on the exponential loss function. Second, in error correction. Gradient boosting focuses on predicting and correcting the errors made by the previous model, leading to a more robust learning process, while AdaBoost focuses on assigning weights to training examples. It increases the weight of misclassified examples in subsequent iterations, forcing the weak learner to pay more attention to them. And lastly, in their approach. AdaBoost has a sequential approach wherein weak learners are trained one after another, with each focusing on examples that the previous one struggled with. Gradient boosting, on the other hand, has an additive process where each weak learner builds upon the errors of the previous ones, progressively improving the overall model. As a simple analogy, in AdaBoost, imagine a teacher focusing on students who got the previous test wrong by giving them extra help. In gradient boosting, think of a group project where each team member builds upon the work of the previous one, which makes the outcome better.
So, how are decision trees used in gradient boosting? Gradient boosting typically uses short, less complex decision trees instead of decision stumps. Here, many weak learners, which make up the individual decision trees, form one strong learner. Every tree is connected in series, and each particular tree attempts to minimize the error of the previous tree, that is, the residuals. Doing this makes boosting algorithms slow to learn but highly precise. A loss function is used to determine the residuals from each step. For example, a user could use mean squared error for a regression task and a logarithmic loss for classification tasks. In gradient boosting, decision trees are typically the chosen weak learners due to their simplicity and efficiency in learning local patterns. Each new decision tree focuses on the areas where the previous models made mistakes, leading to a more robust overall model. So let's analyze the relationship between decision trees and gradient boosting. Imagine you're navigating a maze. You seem lost, confused, and really don't know where to go. A single decision tree is like one explorer taking a single path. It might be inefficient or lead to a dead end. Gradient boosting is like having multiple explorers try different paths simultaneously. Each learns from the mistakes of others, eventually leading you to the exit more effectively.
In order to really analyze the gradient boosting method, let us relate it to the words we always hear, which is learning from mistakes. So, for this example, given the situation where there are students who are weak learners, having an initial assessment for the teacher to gauge their overall understanding by giving a simple test. This provides a baseline performance. Since the teacher now has the prediction for the initial assessment, she identifies the mistake made by the students. And here is where the learning from mistakes will kick in. As the teacher is now fully aware that the students have made mistakes on particular questions, she then creates a new lesson plan that specifically addresses these errors. With the lesson plan that has been made, it is now more understandable and only consider a few features relevant to the mistake made by the students. After students learn the lesson plan, they combine their overall understanding with the new acquired knowledge, which will address the error. By repeating the steps multiple times, each time creating a new lesson plan based on the set of errors, the student will be able to become more confident and better at identifying and correcting their mistakes, which lead to the improved overall performance. With that being said, gradient boosting is a powerful tool as it combines many weaker learners to make strong learners. So, to deeply understand, these are the steps on how gradient boosting can be learned. Step 1: Initial model. It is by having a simple model, often the average of the target variable, which would be the initial model providing a baseline prediction. Step 2: Error identification, in which the algorithm calculates the residuals highlights where the initial model made mistakes, which represents the difference between the actual values and the initial model's prediction. Step 3: Targeted learning. Now that it identifies the mistakes, gradient boosting creates a new model that specifically focuses on these residuals. This new weak learner aims to capture the patterns in the data that the initial model missed. Step 4: Weighted combination. The predictions from the new model are not directly added to the initial model. Instead, they are weighted to prevent overfitting. This weighting balances the influence of the new learner with the initial model. The combined prediction becomes the new assembled model's output. Lastly, step 5, iteration for improvement. Step 2 to 4 are repeated iteratively. In each step, a new decision tree is built focusing on the residuals of the previous assembled model. With each iteration, the assemble learns to address the shortcomings of the previous model and gradually improving its overall accuracy.
Moving on to what parameters can you adjust. In gradient boosting, a powerful ensemble learning technique, several key parameters can be adjusted to optimize model performance and mitigate the risks of overfitting and underfitting. The learning rate, also known as shrinkage, governs the contribution of each tree to the final ensemble. Lower values typically necessitate more trees but can enhance generalization. Conversely, higher values may lead to overfitting. The number of estimators determines the total trees in the ensemble. While a greater number of trees can improve performance, excessively large ensembles may suffer from overfitting and increased computational costs. Additionally, controlling the maximum depth of trees is crucial. Deeper trees can capture intricate patterns in the data, but overly deep trees may overfit. Parameters such as minimum sample split and minimum samples leaf regulate the complexity of the trees by specifying the minimum number of samples required for node splitting and leaf formation, respectively. By increasing these parameters, the model tends to generalize better and mitigate overfitting. Finally, limiting the number of features considered for splitting via the max features parameter can aid in preventing overfitting, especially in datasets with high dimensionality. Overall, careful tuning of these parameters is essential for achieving an optimal balance between model complexity and generalization performance in gradient boosting.
Moving on to why tuning matters. By adjusting these parameters appropriately, you can fine-tune the gradient boosting model to achieve better performance while avoiding overfitting or underfitting. Experimentation with different parameter values and evaluation of their impact on model performance are essential for achieving optimal results. Tuning in gradient boosting is crucial for optimizing model performance. It involves adjusting parameters such as tree depth and learning rate to control model complexity, prevent overfitting, and improve generalization. Tuning also speeds up training, tailors the models to specific datasets, and addresses challenges like imbalanced data. Overall, it's essential for building accurate and reliable predictive models. Moreover, the iterative process of tuning fosters a deeper understanding on the underlying data and model dynamics, empowering practitioners to make informed decisions and extract actionable insights from their predictive models.
After figuring out how we are able to tune the gradient boosting method, let us now look at some of the pros and cons of using this machine learning algorithm. First, let us look at some of the advantages. The gradient boosting method is an effective framework or method for achieving high accuracy selecting and estimating predictors, particularly when dealing with complicated and large-scale data. It can recognize complex patterns and relationships within the data and also manage mixed models without the need for pre-processing these data types. Furthermore, because it can handle both regression and classification problems, it is a very flexible method that suits a varied range of coding applications. It also requires less computing power and training time as well, making it an excellent choice anytime unstructured and chaotic data is involved. Finally, it is advantageous because gradient boosting with decision trees can accommodate missing values in the data by employing surrogate splits in the tree's building process, thereby creating alternative paths for predictions to occur. However, it is worth noting that handling more complex data also requires a more complex algorithm. Unlike decision trees and linear regression models, gradient boosting requires a deeper understanding of machine learning concepts as well as its limitations. Imbalances with datasets can also cause even more complexity to happen due to additions of even more algorithms. Problems like having low convergence rates, erroneously generated shrinkage, and the said imbalanced effect selection are also some of the shortcomings of gradient boosting. In addition, there are unequal settings and skewed random impact estimates. Additionally, when the dataset is small and the model is very complex, it is also prone to overfitting. But by modifying the gradient boosting to a nonlinear configuration, it can be stabilized as these specific regularization techniques are employed.